lipid droplets fluorescing inside the cells, and these are the cells when viewed under scanning electron microscope. The major fatty acids usually found in this yeast lipids are palmitic acid, stearic, and oleic acid. So, but production of biodiesel from yeast-based sources is not economically viable, since there are a lot many steps, pre-treatment and then extraction and trans-esterification. So it is always preferred that it is co-produced with other value-added products in a biorefinery approach. So this biorefinery approach, it comes from similar to the petroleum refinery, where one crude we get and it's distilled to get different range of products. So similarly in biorefinery, using a single feedstock, we get a different kind of products. So the first step in a typical biorefinery model is the selection of a suitable feedstock. So like animal waste, lignocellulosic, and this will determine like what kind of pre-treatment we will do after that, and followed by the process optimization, one of the most critical steps in any bioprocess or product development. And the different methods used are trans-esterification, biochemical methods, and sometimes thermochemical methods like gasification or pyrolysis, and followed by the valorization of the produced waste streams of the process. So if we can valorize the produced waste into some value-added products, so we can have some economical advantage in the process. The different products that we can get are biodiesel, bioethanol, biocrude, etc. So this is the schematic which shows that what are the possible products that we can obtain using yeast as a feedstock. So here I have used glycerol as the carbon source, and after the yeast is cultivated in a bioreactor, the broth was harvested and it was then flocculated, and the intracellular products will have lipids from where we can get biodiesel, and carotenoids will have applications in cosmetics and other healthcare products, while the de-oiled fraction, that is it's almost kind of waste, which is usually discarded after the extraction of lipid, can be valorized to produce biocrude, biochar, light organics, or even animal feed applications. And the cultured supernatant, which will have the extracellular products like enzymes, bioemulsifier, and alcohols. So these are the possible products that we can get using yeast as the feedstock. So this is the process flow diagram of the yeast biorefinery, or the work that I have performed during my PhD. So we have cultured the yeast in a shake flask and optimized all the process conditions, and then all the optimal conditions were validated in a 3.7 liter lab scale bioreactor. And after the biomass was harvested, the cell disruption was performed by using ultrasonication, and the direct trans-esterification method was used. So I will talk about it in details in the coming slides, where the neutral lipid fraction was selectively converted to the fatty acid methyl esters, and the recovered de-oiled biomass, which I mentioned, which contains good amount of protein, carbohydrate, and also some amount of lipids, was used as feedstock for the HTL or hydrothermal reaction for the production of biocrude. So this is a precursor of some advanced biofuels, and this can be upgraded to form fuels in the jet fuel range. So coming to the first step, this is the standardization of the physicochemical parameters for the improved biomass production and lipid yield in the oleaginous yeast. The most critical and first step we can say is the process media optimization. So which includes the development of a two-stage inoculum and selection of the right nitrogen source, which we want to identify the right kind of nitrogen source which can be easily utilized by the yeast, and the initial carbon to nitrogen ratio of the media. So for yeast, it's very much known in literature that nitrogen limitation is known to enhance the lipid accumulation in yeast. So that's why we have chosen this as a parameter. And next is the process standardization, where the volumetric oxygen transfer rate assessed in terms of KLA was measured. And then all the optimal conditions were validated in the reactor conditions. And then the biomass was harvested, and we obtained this biodiesel after trans-esterification. So as I mentioned that nutrient limitation or mainly nitrogen limitation causes lipid accumulation in oleaginous yeast. So this pathway it shows how this flux is driven towards the lipid accumulation. So what exactly happens inside the cell? So when the media nitrogen is exhausted, the enzyme AMP deaminase gets activated and the level of AMP decreases. So this in turn inhibits the enzyme isocitrate dehydrogenase. So isocitrate is converted back to citrate and it is funneled out of mitochondria where it is acted upon by ATP citrate lyase. This is one of the key enzymes in any oleaginous yeast to form this acetyl coenzyme A, so which via fatty acid synthesis pathway contributes to the formation of neutral lipid droplets in the ER membrane. So this is how the flux gets diverted when the media nitrogen is limited. So these are the strategies that was adopted for the improved biomass density and lipid content in yeast. So first is the standardization of the inoculation media and then the nitrogen source and C/N as I have mentioned. And the KLA, which is usually done in a reactor, but I have done this a systematic set of studies in shake flask to reduce the number of runs in reactor. So for this, what I have done is I have varied the media volume from 50 ml to 200 ml in a 500 ml flask so that the height or headspace inside the shake flask is different for all these flasks. And the KLA was calculated using an empirical equation following the method by Mayer et al., where we take into account the agitation frequency, the working volume, the shake flask diameter, and the incubator shaking diameter. So all these things were taken into consideration, and the KLA was maximum for the minimal filling, that is 50 ml flask, and it was around 0.8 minute inverse. And so we just validated these conditions again in a reactor, and in reactor we calculated KLA by the dynamic gassing out method, and we found that it resulted or enhanced the biomass density as well as the lipid content. So this table shows the stepwise improvement in the biomass concentration and lipid productivity upon these optimization strategies. So in reactor, we see around 40% enhancement in biomass density, and for lipid productivity, it is around 77%, which as compared to the baseline study. So all these strategies used to be useful, and it improved our yield for the biomass and lipid. So this work was published in Bioprocess and Biosystems Engineering. And the next step is the different downstream processing steps involved. For extraction of any intracellular product is one of the most critical steps. So the different steps involved in downstream processing are the harvesting of biomass, drying, cell disruption, extraction, and transesterification. So harvesting of biomass is one of the most crucial steps because it accounts for 90% of the total biodiesel cost, and it's done by either centrifugation or either filtration. So both these methods are energy intensive methods, and we are not sure whether it can be employed in large scale applications. So we used flocculants like chemicals or biopolymers. For my work, I have used chitosan, which is a cationic biopolymer, and it resulted around 80 to 90% of cell separation. The next step is biomass drying, and we use either hot air oven for solar drying. Again, hot air oven is a energy consuming process. Solar drying is a time consuming process. So what we did is if we bypass this step altogether, if we use the wet biomass directly for cell disruption, we can save considerable amount of time and energy. And for the different cell disruption techniques are using chemicals like acid alkalis method for disrupting or destabilizing the cell membranes. But this poses hazards when these chemicals are released into the environment. While biological method uses the enzymes such as lipase, and unless these enzymes are immobilized, it's not economically viable. So we can use mechanical methods like sonication, bead beating, or homogenization using either high pressure or high speed homogenization for disruption of the yeast cells. Lipid extraction is the next step, and here different kinds of solvents are used for extraction of total lipid and then neutral lipid, which will be then transesterified to biodiesel. So since there are this many number of steps, this may lead to product loss. So our idea was if we can do some process intensification where we can combine these three steps together into a single step, we can save time, energy, as well as make it economically viable. So this is the schematic of the direct or in situ transesterification, where we have used wet biomass slurry, and this was directly subjected to cell disruption and transesterification, where the reagents for transesterification like sulfuric acid used as catalyst and methanol hexane were added to the disrupted biomass, and the neutral lipid fraction was selectively converted to the fatty acid methyl esters, which was then analyzed in gas chromatography by gas chromatography. So this is the like the strategies that I adapted. So here like different cell disruption techniques I have studied, like sonication, beating, homogenization. From this image you can see that this is the control A. You can see the intact cells, and C and D are the sonication and after beated images, so completely disrupted cells. So it suggests that these methods are well suited for yeast cells, and the results are again cross-checked by viewing the cells under fluorescence microscope. So here also is I see intact cells where the lipid droplets are fluorescing inside the cells, and here it gives some cloudy appearances, suggesting that cell disruption has taken place. And next, the critical in situ transesterification parameters were optimized, like biomass to methanol ratio, how much methanol should we add, the catalyst concentration, the sulfuric acid I have used, and the reaction time and temperature conditions. And then it resulted in improved yield. We achieved around 90% FAME yield after the optimization studies, and the FAME was characterized by gas chromatography and the properties were computed. I won't show all the results in details. I just want to show the little energy analysis that we have performed. So this shows the energy or comparative energy analysis between the conventional transesterification and the direct method. So for processing 1 kg of yeast biomass, around 85 kilowatt hour of energy consumption was recorded, and for direct method it is around 41 kilowatt hour, which is almost reduced to half. So this process can be suitably scaled up for industrial application. And so this states that 1 kg for processing of 1 kg biomass, the energy consumption was reduced by 51% and cost is reduced to around 6.68. And we published this work in RSC Advances journal. The next step is the valorization of the waste. So after the lipids are extracted and converted to biodiesel, the residual biomass, which contained a good amount of carbohydrate, protein, and some residual lipid amount, was used as a feedstock for hydrothermal liquefaction. Usually this is usually discarded or used for low value applications like animal feed. So here we try to produce another high value product, that is another fuel called biocrude. So this is a advanced fuel and it can be upgraded in the jet fuel range. So this work was done in collaboration with the chemical engineering department of IIT Madras. And this is the strategies that I used for this study. And the first is the characterization of the feedstock by approximate ultimate analysis and calorific value, and also the thermogravimetric analysis. So this was done to identify at what temperature maximum decomposition is occurring, so that we can accordingly do our experiments. And the HTL reaction conditions were also optimized, like the temperature and pressure conditions. And the co-solvent, I have used glycerol as a co-solvent here, so which is also the transesterification byproduct in the previous step. So it is known to enhance the biocrude yield as well as the quality of the biocrude. And then it was followed by the product separation and characterization of the products in terms of FTIR, GCMS, and elemental analysis. And so I'll just talk briefly about what this hydrothermal liquefaction is. So it involves a thermochemical process, obviously, and it involves a temperature of around 200 to 400 degrees Celsius and high pressure of around 50 to 200 bar. So this shows the pressure temperature profile of the water. Here you can see above 100 degrees Celsius and below 374 degrees Celsius, which is the critical point of water, is the subcritical liquid region. So the liquid state of water here is being maintained by the high pressure. So here water itself acts as an organic solvent, and it's not essential to add any catalyst or other organic solvent. And the process is very much similar to the geological formation of fossil fuel, and the major advantage here is it can be formed in minutes as opposed to the fossil fuel which requires thousands of years. And actually what happens in the hydrothermal liquefaction, the depolymerization of the different fragments inside the biomass like the proteins and carbohydrates take place, which again repolymerizes back to form a more homogeneous kind of compound, that's a biocrude, and it can be upgraded to advanced fuels. There are two conventionally used thermochemical processes like the pyrolysis and liquefaction, and liquefaction has certain advantages over pyrolysis, and most importantly here drying step is not required. Also temperature is moderate as compared to pyrolysis. Also the calorific value of the products in terms of HHV is higher, and when we get in talk about liquefaction with lesser oxygen content and water content, although the viscosity of the product is little high in liquefaction. So this is the reactor that I have used at IIT Madras. So this you can see, this is the like the reaction vessel where all the components were kept, and the outside is the heater, and it's attached with a temperature probe and impeller. And after we are loading the biomass, the inside air was purged out while we insert purging with nitrogen, and the initial pressure of around 20 bar was maintained inside the reactor. And after 30 minutes of reaction time, it was allowed to cool down and all the products were separated. So this is the actual photograph of the reactor. And I have tested the different operating conditions and pressure at 260, 280 and 300 degrees Celsius with and without using glycerol as a co-solvent, and I have used feedstock percentage of 7.5%. And this shows the energy balance in the HTL reaction. Since it is a energy intensive process, so energy balance must be performed to see whether we have a positive energy output, because the energy that we are using, the input energy, it comes from fossil fuel. So whether there is a process have a positive energy output must be calculated before we proceed further. So this shows that the energy recovery ratio, which is the calorific value of the product divided by the calorific value of the feedstock, and this shows that the process have a positive energy output, which is also relevant by the energy conversion ratio, that is the ECR. This is the energy required for the liquefaction process divided by the energy of the products. And this is the image of the product separation. So the bottom phase is the biocrude, which is dissolved in dichloromethane. I have used this as a separating solvent, and the top phase is the aqueous phase where also some organics are dissolved. And we published this work in Journal of Cleaner Production. So coming to the fourth step, and it's the last step of my work. So I have done a detailed life cycle analysis study, and nowadays it has become mandatory for any bioproduct development to do a LCA study to gauge the environmental impact from the process. And the inputs from all these processes have been taken into account for the production of biodiesel and biocrude, and this was done in collaboration with the civil engineering department of our institute. And in the LCA methodology, it comprises of a goal and scope definition, inventory analysis, where all the inputs and outputs from each of the processes has been taken into account, and followed by impact assessment and interpretation. So I have used the software CIMA Pro version 8, and the method I have used is recipe endpoint H method, and in a cradle to gate approach. So cradle to gate means here, so from the extraction of natural resources up to the development of the product till the factory gate. That's how the name comes. And I have used the functional unit of 100-liter biodiesel. The goals of this study was to evaluate the sustainability of the biodiesel and biocrude production process by analyzing its life cycle, to get a quantitative estimation of the environmental impact categories, to identify the key processes contributing maximum to the overall impact. So this is the system boundary. So before any LCA study is performed, a system boundary must be defined. And so for this study, this is our system boundary. See, I have taken into consideration all the steps that I have talked previously about this cultivation of yeast, yeast, and then harvesting using chitosan and cell disruption and trans-esterification and HDL steps. So my two main products, the primary products, are FAME biodiesel and biocrude. So the red lines indicate the inputs and the blue lines indicate the outputs from the system, while the dashed line you see is the recycled stream. So the trans-esterification byproduct is glycerol. So I have used glycerol as a carbon source in the cultivation of yeast study and also as a co-solvent in the HDL reaction. So this is the life cycle impact assessment method. So I'll just explain it very briefly. So there are different midpoint categories, around 17 midpoint categories, like this: ozone depletion, climate change, ecotoxicity, etc. So what happens when we give our inputs, like what are the inputs to the system? The software calculates it based on the different midpoint categories. So for example, for climate change, it will calculate based on the amount of CO2 emissions or amount of methane it emits, and it gives it in the GWP or global warming potential, and which are then results of this midpoint categories are then aggregated to form these endpoint categories, and which are also called the damage categories, like human health, ecosystems, and natural resources. So this is how the results, like what you're giving, will be translated to the impact category indicators. So these are some of the results I just like to share with you. So these are some absolute values of climate change and resource depletion. So we can see that climate change for cultivation of yeast sape, it is very high, and resource depletion is very high for trans-esterification and cultivation of yeast. So primary reason here is for yeast cultivation, we have done it in reactor, and we have used input energy for which comes from the fossil fuel. So Indian mixed electricity mix still constitutes around 60 to 70% from thermal plant. So that is why it shows negative impact on the environment. And the second, this graph, it shows a comparison of the damage assessment of the sub-process. Here also you can see the green line is the HDL or hydrothermal liquefaction, which shows negative impact on human health and ecosystems, while trans-esterification, it shows some impact on resource depletion. So this actually LCA study suggests that what are the steps where we need to improve upon further to have a lesser environmental impact. So this study must be performed nowadays for any kind of byproduct we develop. And recently we published this work in Journal of Linear Production. So that's all. Thank you.
Thank you, Dr. Jayata, for this wonderful talk. And now there are many questions from participants. So I can ask only few questions.
Yeah, sure. Please go ahead.
So there is a first question. Is there any difference between yeast-based biodiesel and microalgal biodiesel?
Yeah, if you talk in terms of composition, there is not much difference, but both algal cells have already been, they are growing it algae in industrial scale, while yeasts have not been taken into that scale yet. So we we don't know whether how well this competitiveness this yeast cells will do. But in terms of, I can say that yeast cells has advantages in terms it's not dependent on environmental conditions. So you can easily grow it in any closed environment, and even nowadays they are trying it growing in open ponds, because certain yeasts it can grow even in lower pH like 2 to 3 pH. So the chances of contamination also is very less. So if we can do it like this, then there is no better way than that. We will have a very less energy input, and we can get a very high lipid yield from it.
Okay, so according to you, which one is economic, yeast-based biodiesel or microalgal biodiesel?
Currently, both are not that much competitive with petrodiesel, because yeast-based biodiesel, I think in some studies I have seen, it is around 120 to 130 rupees per liter. And similarly for algal-based biodiesel also, it is around 150 or 160. And we can further increase upon it, but still it's nowhere comparable to that of petrodiesel.
Okay. So next participant asks one question. Can we use such biodiesel for our car IC engine? What modification can make to use for vehicles?
For vehicles, yeah, see, so with that, for that we have to do some engine testing, but I have done some studies based on deriving the computing the biodiesel properties like the viscosity and the C10 number and all. And if we mix it in like 20 to 30% like B20 B30, there is no such requirement to change the engine configuration right now. But B100 or B 80, if you try to use, then we cannot use in the existing engine configuration.
Okay. And there is a next question, like another participant asked, what about mass balance in STL process?
Yeah. So mass balance means like what we are putting and how much we are getting. So I have showed in my presentation that it's it has some positive output. So like more than mass balance, energy balance is relevant in case of hydrothermal liquefaction, because this process requires high amount of input electricity, and which I mentioned are obtained mostly from fossil fuels. So how much is the calorific value of the products that we have calculated, and we found that it has a positive energy output when compared to what we are putting inside, like how much energy is consumed. So it's a process is feasible in terms of energy feasibility.
Okay. So another participant asked that how much yield you have been achieved for your case
For
for
bio
biodiesel?
uh,
Yes, biofuel.
for biodiesel, our FAME yield was around 90 to 92%, like amount of FAME obtained by the amount of lipid which was there inside the cell. And for biocrude, it was around 50 to 52%, like amount of yeast feedstock we have used, how much amount and how much amount of crude we obtained from it. It was around 50 to 52% for biocrude.
Okay, now there are many questions also. Participant has asked. I asked some few of them. What factors have been considered for LCA study to evaluate sustainability of biodiesel?
What factors that we considered?
For LCA study to
Uh,
evaluate sustainability of biodiesel.
Yeah, so actually this LCA study, it determines whether the entire process is sustainable and whether how much impact it has on the environment. So we take into account all the inputs in the process, like what we are using for cultivating the yeast, and well as for transesterification and different steps. What are the inputs? So all these things have been taken into consideration, and we get the results based on the impact categories. So this suggests that how much sustainable is the process. So if it is no, but all these results that we show are no, it's our normalized results. The actual values are usually not given, because then we cannot compare, because all units are different. So the normalized values are given, and it says that which factors need to be further improved or optimized to have a better environmental impact.
Okay. And there is another question from participant. Which pre-treatment method can be preferred for biodiesel production from biomass?
So no, that depends like what kind of biomass we are using. So if it is lignocellulosic biomass, there are a lot of pre-treatment methods that needs to be done. Like usually they do hydrolysis or autoclaving or acid hydrolysis or even alkali hydrolysis. So I have personally not worked on lignocellulosic biomass, but
Okay.
for algal based and yeast based biomass, so since yeast cells are somewhat rigid, it contains some chitin microfibrils, so it needs to be destabilized before the lipids can be extracted from it. And I showed that I have tested different mechanical methods for it, and I found that sonication was better and compared to the other mechanical methods.
Okay. So thank you very much, Dr. Jayata, for this
Thank you.
wonderful talk. And like you have given very inspiring lectures on the biodiesel production and biofuel productions. Thank you very much.
And thank you for having me. Thank you.
Yeah. So our next speaker is Dr. Vivek Rangarajan. Dr. Vivek Rangarajan is currently working as an assistant professor in the Department of Chemical Engineering, BITS Pilani, Goa campus. He started his career as a lecturer in Sastra University, Tamil Nadu after graduating his MTech in Industrial Biotechnology. He completed his PhD from IIT Kharagpur. Subsequently, he worked as a postdoctoral researcher at Stellenbosch University, South Africa. He is currently supervising 4 PhD.
Yes, I'm listening.
He has published his research works in both national and international journals. After joining BITS, he has been awarded with 2 funded projects. Dr. Deepak. So without delaying, we go to our speaker. So Dr. Deepak, can you listen me?
This is Vivek. Hello.
Sorry, Vivek. Dr. Vivek.
Yeah, I think you're mistake. Yeah.
Yeah, sorry. Can you listen me?
Yeah. So I can listen you. So
I can see your PPT. That's good. Okay, you can start your presentation. It's over to you.
Okay, thank you so very much, Dr. Piyush. And first of all, I would like to thank the organizers of this workshop for having arranged, such a common platform for all researchers, experienced as well as upcoming researchers like me to share our research works amidst, the kind of global lockdown. And I hope, it would be very much useful to delegates as well who are, aspiring to become, a good researcher. So the topic which I'm going to present on for today would seem to be a bit off the track from, the proposed, theme of this workshop, that is waste to bioenergy. Because I'm going to present on the application of biotechnology to increase soil recovery. So you have been attending to lectures which were focusing on, the making bioenergy from biomass by different means. But in comparison to that, so my topic is a bit different. But I hope you would acknowledge at the end of this session, you would also appreciate so that this topic comes well within the realm of bioenergy, so well within the realm of biotechnology. Okay, so the topic is microbial biosurfactants for the enhanced oil recovery. So as you all know that crude oil, crude oil, it remains to be the, prime mover, at least for another 3 to 4 decades. So though, we are seeing all efforts from different areas to fill the gap in a way that to augment, the current deficit, which cannot be met by the crude oil towards different demands. So we are in fact trying to replace, find a viable alternative for the replacement of crude oil. But I hope that still we have enough reserve of crude oil which would last for, say, at least 3 to 4 decades. Okay, so these are the contents which I'm going to focus on. So I would start with what is crude oil and how it is formed, and different recovery methods we have in place that are currently being adopted to recover the crude oil beneath the earth. And my major focus would be on the application of biotechnology in enhanced oil recovery. So we use a popular term called microbial enhanced oil recovery, so which is what I'm going to dwell upon for some time. And then my actual area of interest is biosurfactants, So we produce and purify biosurfactants, using it for different applications. And I would also give my perspective on the intensified processes that we develop for improved production and purification of biosurfactants. And I would conclude with the few trials that we carried out in a lab, so with the use of biosurfactant and biopolymer cladding for the enhanced oil recovery. Okay, so it would be, I think most of you know that what is a crude oil and how it is formed. And so I would say that if you believe in the evolution and further you accept the fact that all the species are related to each other, somewhat related to each other since their inception and up till now, you should also accept the fact that the crude oil is a gift, so which is obtained from our ancestors. Okay, so it all happened, 300 to 400 million years back. So when the dead biomass, say it can be plants or animal biomass, so when they settle deep down, the ocean, so when they settle on the bed, so it was covered with different layers of sand, silt, shales, the so-called different, sedimental particles as they accumulated over them. And as you all know that it underwent a lot of transformation. So, but if you look at the time scale, it took eons of time, a long time, in fact, more than 300 to 400 million years. So over course of time, what happened was all these dead biomass got fossilized, and over the course of time, due to the tectonic action, so what you call as movement of plates and the rubbing of various stratum of these plates created a lot of temperature and pressure, say, due to the frictional force that resulted in the formation of oil. So what you see now as kind of a black gold that we still are able to recover, so deep beneath the earth is so nothing but a fossil fuel, so which our ancestors have given us. So if you take a barrel of crude oil, so these are going to be the components present in it. You see about a third of it is diesel fuel, and nearly 27% of it is petrol, and you have also about 15% of liquefied petroleum gas, and rest comprised of fuel oil, naphtha, kerosene, other products which we use to make petrochemical products, the common day-to-day products such as plastics and the detergents that we use for household applications. So all these are the products from the crude oil which our forefathers, ancestors have given us. But what is alarming more than the discovery of crude oil, if you just look at the time it has taken for the generation of crude oil, so it really took a long period of time. Say, I would say describe in terms of eons, so 300 to 400 million years. It's not a small period of time, but as compared to this, the rate at which we deplete or try to finish it off is very fast. Which is what is presenting as a very alarming scenario. And so this is where we are trying to fill in gap by bringing in the other sources of energy, and the upcoming being the bioenergy, which most of the researchers are aiming for, like bringing up a new types of fuel and adding value to the existing biomass. So that is what we are aiming to do. But so this scenario that we see, the rate at which we are depleting this crude oil is really presenting as an alarming scenario. So so if you ask me, like, what is the current availability of the crude oil, so which is estimated in terms of the reserve potential, so it is about 1.65 trillion barrels. So this amounts to 1.65 into 10 power 12 barrels. But if you look at the consumption, the rate at which the oil is consumed is slated at 35.4 billion barrels. So 35.4 into 10 power 9 barrels. So, so one barrel is equal to 159 liters of crude oil. So if you take the ratio of this, so we are left with only the crude oil which would last say for about 46 years. So so this is not going to be like a kind of a simple scenario, because we see the daily rate of oil consumption is increasing. So that is why we are trying to address this deficit in oil, demand by fulfilling it through other energy resources. Okay, so these are the countries so which have the vast reserves of crude oil. So they are clubbed under an organization called OPEC. So OPEC countries, they hold the maximum. In fact, 4/5 of the crude oil is being like handled by the OPEC countries. The rest would be shared by other countries. It's only 1/5 is shared by the non-OPEC countries. So if you see the major producer, the current major producer of crude oil, USA ranks first, followed by Saudi Arabia and so many other countries. But so India accounts for crude oil production, it accounts for only 1%, because we are still exploring the reservoirs where we can produce more crude oil. And there are, how this crude oil is located. Okay, so there are the geologists and the oil explorers. They have identified, so with their experience, they have identified different types of faults on Earth. So which they use as major indicators for finding crude oil. So these are the two types of faults in Earth. One we call it as anticline. You can see, which is characterized by a mound-like structure. So you can see a capped rock. Beneath it, you can locate a crude oil filled with gas, the top of it filled with gas, and below which you can see water. And the second type of structure, in which the likelihood for the presence of crude oil is more, it is faulted rough. Again, you can see here the various layers of rocks, one over the other, below which you can find the crude oil and the gas. Okay, so these two are considered to be the major the traps for locating the crude oil. And if you look into the methods, different methods that are currently being adopted to recover this crude oil, so you can categorize them into three. So, so primary recovery, so I will shortly talk about it, accounts for 10 to 25% of recovery, and followed by secondary recovery, which adds up another 20% of crude oil recovery. So, so what as the biotech researchers we are aiming for is contribute to this tertiary recovery. So, which accounts for the remnant oil which is not possible to be recovered by the primary and secondary recovery operations. Yeah, so this is how this primary oil recovery works. So, as soon as you are drilling hole beneath the earth and try to reach out to the place where crude oil is present, the initial fraction of oil gushes outside, resulting from the natural reservoir pressure. So you don't have to invest in any energy to bring out the initial fraction of oil, which I said about 10 to 20%. So it simply, comes out by the existing reservoir pressure. So which accounts, as I said, for 10 to 20%. So once the pressure, the reservoir pressure becomes equal to the pressure at the bottom of the, the well, your primary recovery stops. That means you no longer get, the oil coming out through the natural pressure. So so this is a stage we switch to secondary and tertiary oil recovery procedures, where we try to pump in liquid from other side of the well. So the well that you're seeing here is called the production well because so this is a well which is used to recover the oil. But when you want to switch to other types of recovery options, say secondary or tertiary, so you need to inject, you need to drill other wells at the surrounding this, the primary well for injecting, various other fluids. Okay, so that takes us to, the secondary oil recovery. So when the primary recovery is no longer sustainable and the natural pressure has completely gone down. So we resort to secondary oil recovery options. So here you can see the vicinity of your primary production well. You see the secondary wells, which are called injection wells. So through which we pump in the different types of liquids. A simple liquid is water. There are also ways by which steam can be injected, steam which is generated as, so by utilizing oil from the reservoir, and various other solvents, acids, gases can be pumped in. So depending upon the type of oil and, the pattern with which oil is distributed, beneath the earth's surface. So we use a different combination of secondary recovery options. So which is going to recoup, say, it's about another 20 to 30% of oil. And so when both these recovery options, they meet their demand when they serve the purpose. So we still have a remnant oil of about, say, 50%. So which becomes so very difficult because this oil, unlike the oil which was recovered in previous recovery stages, say primary and recovery, so they are tightly held by the capillary forces. So you will find below the earth's surface a huge amount of oil is still trapped in, despite the secondary recovery option, so which can be only driven out with the help of tertiary recovery option. So if you look at the tertiary recovery options, it's also called improved oil recovery schemes. We have different varieties of methods, all of which so they are tried out, by trial and error. Only the geologists and oil explorers can know, can tell you so what method would be suitable for that particular reservoirs. But the contribution from biotechnologists are tremendous in this field. So we call them as microbial enhanced oil recovery. So which is naturally happening. So once after the secondary recovery is done, so you will see microbes. So they do their roles in improving the oil recovery. So we primarily adopt two types of enhanced oil recovery methods, so which are categorized as ex situ microbial enhanced oil recovery, where the microbes are injected from outside. It can be microbes or products of the microbes injected from outside into the wells, and they are going to play some roles which would facilitate the recouping of the oil which is unrecovered from the primary and secondary treatment operations. And the second approach is in situ oil recovery, under which we try to stimulate the indigenous microorganisms. So which are present in the native reservoir. We try to biostimulate them by feeding some nutrients, cheaper nutrients, cheaper substrates to them. So, but both these cases would require that well to be shut off for some period of time, because you want, as you know, this biological processes are, designed to be very slow. Inherently, they are very slow. So, so you allow that you allow this process to take place by shutting down the well, say after injection of microorganisms, either by ex situ or activating the in situ microorganisms. So give some time for these microbes to start its action. So these are the following mechanisms by which the microbes facilitate or improve the oil recovery. So which I'm going to discuss in the next two slides. So one is a selective plugging. The second one is the wettability operation. So there are other mechanisms or the processes by which the microbes or the products of microbes can facilitate this oil recovery. So injection of bioacids, again this come under XC2 MUR process, degradation and cleaning of buildup of oil. And so we have recently entered into the use of genetically modified microorganisms, so GMUR. And then the another method is the enzyme enhanced oil recovery, so which is CEMOR. So coming to this selective plugging, which is one of the mechanisms by which the organisms are going to play an important role, particularly biopolymer producing microorganisms. So to explain the importance of this selective plugging, so you should know how, so what is the, the pattern of, what is the network with which all, this oil depleted zones and oil containing zones are connected to each other. So while you try to pump in the liquid through the secondary reservoirs to push the oil, you would also find some places which is oil free. So you can see these are the networks which are oil free. So naturally the water which you are trying to pump will go through these highly porous tube zones. Okay, so that means your pumping won't be as efficient, so that takes the fluid through this the channels where oil is present. Okay, so this would become a futile process. But how are we trying to address this is by injecting microbes that can selectively plug these thief zones, the so-called thief zones. You all know these, the microbes, the biofilm forming microbes can do this job efficiently. So when these microorganisms are injected, they are trapped inside these oil-less thief zones, so thereby facilitating the movement of water through these zones where oil is present. So this is how the concept of selective plugging works. So where we make use of microorganisms to improve the oil recovery. So the second mechanism, which sometimes go hand in hand with the other possible approaches, is wettability operation, which in fact is perceived to be the major mechanism by which the trapped oil can be swept out. Okay, so here we make use of biosurfactant producing microorganisms. So in the case of in situ or ex situ oil recovery, so we inject microorganisms that are capable of producing biosurfactants. So upon release, the biosurfactants, they start their action. So as you all know, these surfactants, they are surface tension reducing agents, and they also reduce interfacial tension. And so another important feature is they can emulsify the oil within so-called macromolecular structures called micelles. Okay, so soon after the biosurfactants are released, they try to release this oil which are otherwise strongly held inside the capillaries. In fact, being stopped by these capillary forces, so they release this oil and emulsify this oil, and then it forms a continuous stream of emulsion, what we call as emulsion, which is a mixture of oil in water or a dispersed state of oil in water, so which is made possible with the help of biosurfactant producing organisms. So the other way around is you can directly pump in biosurfactants, thermotolerant biosurfactants, which can do the same purpose. Okay, so these are the two broader methods by which we make use of microorganisms to release these oils which are tightly held between these interstitial spaces, what we call as capillaries. Okay, so this is how the enhanced oil recovery works in this case. So this is a production well through which you are trying to pump out this oil, and this is an injection well into which you are pumping in water or any other flooding agent having biological compounds. And these are the deep zones which are located, so which we are trying to close with by doing this selective plugging operation. Okay, so once you inject microorganisms, they plug this zone, and then you see the oil which are trapped inside these oilless tube zones. So they get emulsified with the biosurfactant and water phase, and then upon subsequent injection of more and more water or the flooding agent, you can recover the remaining amount of oil. But so despite all these efforts, it is not possible to achieve 100% recovery. So you can additionally recoup, say, about 10 to 15% of oil. So we term that oil as, the original oil in place. So if you have identified a field or an oil recovery zone which contains about, say, 100 million barrels, you can recoup, say, approximately 10 billion barrels through this tertiary oil recovery procedure. Okay, so from here I'm going to talk about biosurfactants, which is my area of research. In fact, I'm trying to use these biosurfactants for various other applications, but one such application which we explored is its use in enhanced oil recovery. And as you all know that, so we start the production of this compound in the lab scale reactors, so which is going to be a very much expensive. So the product that you get out of this has to be purified, and there are various hurdles. But we try to minimize the cost of production by using inexpensive raw materials. So here you can see the various types of biosurfactants such as rhamnolipids, sophrolipids, lipopeptide, which is my area of interest and which are used for enhanced oil recovery purpose. So the widely researched being the rhamnolipid, followed by, you can say, the lipopeptide for oil recovery application. So these are the various types of raw materials, low cost raw materials, which are being used for production of these biosurfactants by these producing strains. Okay, so I'm going to talk about this lipopeptide because I've been working on this particular molecule since my PhD time, and I'm also continuing working on this lipopeptide for making cosmetic emulsions. Okay, so to know what a lipopeptide is, it's a compound produced by bacillus species. So we have different types of molecules that can come under these lipopeptides. So as the name suggests, it has a lipid moiety connected to a cyclic peptide moiety, which acts as a surfactant. The surfactant, should have this property of reducing the surface tension, interfacial tension. So what a typical, chemically derived surfactant is doing, the same properties these lipopeptides are also expected to perform. So you have lipophilic moiety at one end, the hydrocarbon chain, linked to a peptide moiety at the other end, so which offers the surfactant action. And these have been tested to be stable at extremes of pH, salinity, and temperature. And they also possess important properties such as low toxicity, biodegradability, and eco-friendly. So which is why we are aiming to use such compounds in the environmental application. And they're also, say, kind of upcoming molecules that have imminent potential to replace these synthetic surfactants. And so they already made a foray into the sectors such as healthcare, cosmetics, food industries, including microbial enhanced oil recovery and bioremediation. So these are two types of molecules which are widely researched upon. One is surfactant, so which has 7 amino acids, cyclic amino acids linked to each other to form a peptide, shorter peptide, and which is connected to a hydrocarbon moiety. And this is another popular lipopeptide called fengycine, whose structure is different from this surfactant. So we have different isoforms of this surfactant, fengycine, or say any other molecules, because you will find subtle changes with respect to amino acids or the number of hydrocarbon chain present. Okay, so if you look at the properties, various properties that one can exploit to generate applications from these molecules. So it is it's a highly surface active compound. That means they're able to reduce the surface tension to a greater extent, and they have very good ability to form supramolecular structures like micelles and vesicles. But the conditions, the environmental conditions it requires would change. Depending upon the environment, you get different conformation of these supramolecular structures, and they are very they have this ability to form profusively. Okay, when these molecules, when you are trying to produce these compounds in reactor, you will see that medium will form profusively, so that in fact that we make use of this property to produce this compound through foam fractionation process, which I will explain to you shortly. And they also act as a good chelating agents because of the fact they have a bidentate group. So two carboxylate groups which can bind to divalent cations like Fe2 plus, Ca2 plus, and Mg2 plus. So they can chelate these compounds. I'll also talk about the perspective why so we are talking about this chelating action. It plays an important role in devising a foam fractionating strategy. So when you're aiming to produce this compound, continuously, and the property which is important to us is the emulsion forming capability. So these micelles can trap in oil. In fact, there is another way of injecting this compound in the form of stable micelles. So upon injection, these micelles, out of their inherent capacity, it can drive in, it can enter, it can allow the entry of the oil into it, forming swollen micelles. So which is what is being exploited in another type of recovery called microemulsion based recovery option. Okay, so now I will share some of the works that we attempted in our lab. So these are the intensification processes that aim to give cheaper products, sustain the production of these products, so which we are aiming to use for different applications. So, so we try to use apply process intensification strategies at various stages of processing. You can use it in the production stage. You can also use it the downstream stage. So I will give an example of each into how we apply these intensification approaches towards production and purification of the compound. Okay, so before getting into production of this compound, so let me first explain to you the need for understanding this foaming dynamics. So like I said, when you start producing this compound in a reactor, you will see that medium will profusively foam. It in fact form uncontrollable foaming. So, and you all know that in case of any valuable molecules, addition of anti-foaming agent is not advisable for twofold reasons. One is that it adds up to the cost of downstream processing, and so many of the therapeutic compounds it is not recommended to add any anti-foaming agent. So so in this case, in this compound which is profusely foaming in nature, so we are trying to exploit this property to design a foam fractionation process, so where you can produce and can competently you can get this product separated from the reactor. Okay, so but the key issues, there are some limitations associated with the foaming process. So one is the unpredictable foaming behavior. Okay, as soon as the foam is generated, you don't know what would happen to its dynamics. Okay, so as it is produced, the foam will immediately collapse. Depending upon the concentration of biosurfactant, the dynamics of the foam would change. And we have also observed that this foam is very much surface active. That means they can easily drain the cells, so which is present in the reactor. So that is one of the key issues to be addressed. The third important thing is, as I explained to you in the previous slide, this lipopeptide can attract vital trace metals. So if your aim is to develop a continuous process, a steady state process, you have to also take into consideration of the rate at which these trace metals are depleted. Okay, so all these issues would disrupt our the steady state production of this lipopeptide, and which we are trying to address by a simple studies, which I will explain to you in the next slide. So to gain insight about the foaming behavior, interaction between the foam with the media components and the time dependent depletion of this foam. Okay, so we started with a simple column study. Okay, so this column, you can see it's a cylindrical column, so which is connected to a sparger at the bottom. It's a very simple setup. It doesn't cost much. Say we just spent 200 rupees in fabrication of this column. The only expensive component in this the foam stability testing is this air rotometer connected. So, and we in fact used the fish tank motor for pumping in gas, which was calibrated. We just calibrated this rotometer. So what we initially started off with is this lipopeptide solution, containing all the necessary components, and then we injected air, and it started foaming. And then we studied the dynamics of the foam, what rate the foam forms, and what is the sustenance capacity of this foam, how long this foaming can last in a typical production process, to get insight about all these features. So we carried out simple studies in this column. Okay, so these are the results of this study. We found that Fe2 plus showed greater depletion. You can see it is continuously dropping as compared to calcium and magnesium 2 plus. So that means you have to replenish the medium by supplementing more and more these vital trace elements if you're aiming for a sustained continuous process. And so on this graph, you can see the cells are also depleting. Okay, so cells are also surface active in nature, so they can easily stick on to the bubble surface, and over the course of time they can come out of the reactor. So we have to devise up a strategy if you're aiming to produce this lipopeptide on large scale using continuous foam fractionation process. So this is how a typical foam fractionation process would look like. So this animation, so that I'm going to show you. So we start with a batch process here. So this is a reactor, and to which we are continuously feeding our substrate containing all the vital nutrients, and over edges of metal ions are also added, and it is pumped in via a peristatic pump. And then first we initiate with a batch growth process, and then soon after your biosurfactant is produced, they foam, and then they come out of this reactor. So this is a vent which is free from any filter, because you in normal reactors you keep filter, the exhaust filter. So if you allow foaming to continue, it would block the filter and it will completely clog, and it would make your entire process futile. So we remove the filter and allow this foam to come out, and in fact we continuously collected the foam out of this reactor. Okay, so what we are trying to achieve through this foam fractionation process is to establish a steady state in the sense you have a continuous pumping in of the media components, while you're continuously extracting your product of interest through the form of foam. So which is somewhat different from a routine, the liquid based fermentation process. If you try to establish a liquid continuous steady state process, so you will see the feed as well as the product that comes out, both are liquid. But in this case, you see the product is present in the form of foam. Okay, so foam is nothing but a gaseous phase present in a liquid phase, in a continuous liquid phase. So that presented us a lot of challenge in establishing a continuous foam fractionation process. But we managed to achieve a sustained production of this product through foam fractionation. Okay, so we varied agitation speed basically, and then we try to see how much the lipopeptide productivity so we could obtain through this foam fractionation process. So we found that at a speed of rotational speed of 300 rpm, so we were able to achieve the productivity of 0.088 gram per liter hour as compared to other agitation speeds, which is So very good in terms of lipopeptide productivity. If you compare this against a batch process, so it would be a tenfold, so less. So in this case, an added advantage is we also concomitantly, so we are trying to extract the molecule, so which doesn't require additional purification procedures, not intensive purification procedures. So what we get as a foam is nothing but the lipopeptide, which is coated, which is presented in the form of foam. So soon after it comes out of the reactor, we collapse this foam, and then we remove the cells, and then so what you get is a lipopeptide in the crude form. So the Molditov analysis of the crude lipopeptide. So this is the lipopeptide which is acid precipitated and lyophilized to dry powder. So when subjected to Molditov analysis, it showed two compounds. One is surfactant and phagicine. In addition to that, we found a lot of impurities. So though you can stop at this stage for using enhanced oil recovery purpose, so I would want to give a brief kind of overview how you can take it forward. So in terms of purification, how we apply the intensification process to get the pure form of product in a single shot approach. Okay, so we routinely employ ultrafiltration for the removal of number of compounds, including enzyme cells. But here we just attempted a somewhat innovative approach to make this purification possible in a very rapid way, and in fact in a single stage we are able to obtain highly pure lipopeptide. So the commonly used strategy is a cross-flow ultrafiltration. As you all know, this cross-flow ultrafiltration, it increases the flux of the liquid. So in the first stage, our aim is to retain these micelles. So to start with, what we do is we dissolve this product in liquid water and then try to solubilize these compounds. So the compounds immediately take a micelle form. Okay, so but these compounds, they are also so if you take the crude lipopeptide, they also have other impurities. Okay, so when you're running the in a simple stage ultrafiltration, you see the micelles are retained because we have chosen a appropriate molecular weight cutoff to retain these micelles as well as the impurities. Okay, so the first stage we try to retain these micelles, and once we concentrate it, so we start this process with higher volume, say about 1 liter, and then upon concentration, the volume would be reduced to say about 100 ml. So it's in fact a tenfold concentration. And the second stage, what you do is we try to collapse these micelles by adding a solvent. So a very simple solvent is methanol. So you add methanol to these micelles, and then you try to break these micelles. So when you break these micelles, you see these micelles are now broken down to its monomeric forms, which are smaller in size, which can easily permeate through these pores of this can say the ultrafiltration. So while retaining these larger macromolecules, in the retentate. So that is how this normal cross-flow ultrafiltration works. It's a two-stage process, but so what we are trying to do is, so in this case, the drawback is, so when you try to use appropriate molecular weight cutoff membrane, you will see that some micelles would be lost. They permeate through this because of its non-uniform size distribution of micelles, so which we don't have control over. So because this is the natural way that these compounds manifest, the shapes that they manifest, they present various sizes. Okay, so you see over course of time during the first stage, you will see the loss of micelles across this membrane. So in order to preserve these micelles, and then you want to make it a single shot purification process, we attempted a very innovative approach. So in this case, so what we do is we add calcium ions. Like I said before, these calcium ions can attach themselves to the bindenddates of which are present in the amino acid chain. So thereby it can size condition the micelles, but the size condition requires one more step which I will explain to you in the next slide. So you can see this calcium added calcium ions, they are attached to this COO minus group. So they reduce the your electrostatic repulsion between the head groups. Thereby, one can pack a more number of monomers into single micelle. So which is what we were aiming to achieve by calcium ion conditioning of this micelle. So once you add calcium ions, so it requires an additional step of keeping this in ultrasonic bath. Okay, so we started off with a non-uniform size distribution of the micelles, and upon giving a treatment of ultrasonication, what you achieve is the size condition. So the micelles, they are of larger sizes. Not only larger size micelles, they are of uniform sizes, which is what is more desirable when you are aiming to purify these compounds. Okay, so
Sir,
hello.
sir, actually, how many slides left, sir?
Yeah, just 2 more slides. I will.
Okay, sir. Thank
Yeah.
you, sir. Thank you.
So these are the results. You can see upon calcium, the conditioning of the micelles with calcium. You can see your size distribution is it got narrowed with respect to the increase in calcium ion concentration. Here you can see it has almost reached the average particle size of say about 80 nanometers, which is what is desirable for this diafiltration approach. So here you can see we have achieved with the increase in calcium ion. So we have achieved a uniform sized micelles of about 79.1 nanometer in hydrodynamic diameter with the polydispersity index of 0.186. So which means that the micelles are in the uniform state, which can be used for to be operated in diafiltration mode. And I think you must have done this type of dialysis in the lab scale for the exchanging the buffer and so on. Basically, you can also use this to separate impurities. So which is what is shown here. So we take the calcium conditioned micelles here, size conditioned liquefaction solution containing some impurities, so to which we are feeding in the calcium chloride solution at the constant rate. So the rate being equal to the rate at which your lipopeptide comes out in the permeate. Sorry, your product impurities comes out in the permeate. Okay, so what really happens is as you start this process, you will see. So we are feeding in the calcium chloride solution to this, and you can see these impurities are slowly washed out, and what is left behind is only this the micelles, which is devoid of any impurity. So it's a very a simple and a single shot approach for the purification of micelles, and so we were able to achieve without any decline in the flux. The flux was almost constant. And over 6 volume passage of 2 millimolar dialysate, we are able to achieve, the lipopeptide of 90.5% purity with respect to surfactant and 95.3% purity with respect to phentersen. Okay, so and then with this we perform lab scale EOR, that means the compounds that we generated from our lab, we produced from our lab, and then so we use something called sand cores to we try to simulate the conditions of the actual oil recovery process in the lab, for which we use the sand cores like this, which are nothing but the excavations that we obtain, the cores that we obtain from the deep stratum of beneath the earth. So we pack that core inside this core holder, and to which we pump in the crude oil just to simulate how your recovery process would look like. So once it is saturated with, we do the primary, secondary recovery operation. So it's a kind of simulation procedure. So after secondary recovery, we inject our compound of interest. That means a flooding agent such as biosurfactant and biopolymer to see what additional recovery we are able to achieve through this tertiary recovery operation procedure. So this is the actual ultimate aim that so we are trying to simulate the condition in the lab scale and we are trying to achieve the improved recovery operation. So with this optimal thing, one can be able to replicate in the actual field, but it requires much more understanding about the actual scenario underneath the earth to implement this. Okay, so all these trials, we carried out different trials under different concentrations of biosurfactant, calcium chloride, change the pH, and we studied the recovery. And so we did CCD runs, central composite, the statistical approach, and then we used the ANGA for predicting what maximum recovery we can achieve. So we eventually achieved additional recovery of about 16% of original oil in phase. So that's it's an example which I showed you. So we used bioproducts, that means biosurfactants and biopolymers, to effecting additional recovery. So what you call as tertiary oil recovery. So with this, I conclude my talk. So thank you very much, and I'll be happy to answer if you have any questions.
Thank you very much, sir, for this wonderful and insightful talk.
Thank you.
So there are a lot of questions, but due to time constraint, I can ask only one or two questions.
Yes.
So, sir,
Please.
actually, the question is that does algae grown in colder region contributes good quality biodiesel? For best quality biodiesel, marine algae is best or freshwater algae?
I think it slightly falls outside my the field of research.
Okay, sir. Okay.
So
sir, there is yes, sir, no problem, sir. There is another questions like what are the factors that can improve microbial biosurfactants for the enhancement of oil recovery?
So actually what we are aiming for is, so far there is no problem with the scaling of the production, and so we are able to achieve a good yield of product, but so we are trying to reduce the cost of production by using a cheaper substrate. So that is in fact the challenging task, because you don't expect the same quality that you get from say the normal glucose based or sucrose based medium from the waste products. So that is going to be the challenging task which so we are trying to overcome.
Okay, and sir, whether other divalent cations may be used for binding the micelle?
Yeah, so you can bind to all types of divalent cations, but at different degrees of affinity, I would say. In that way, like for example, you can also add cadmium. So we have tested this compound for the removal of heavy metals. So for example, cadmium, you can also remove arsenic in the 2+ form, the nickel 2+. So they have stronger affinity to chelate with the biosurfactant. And you can also use a foam fractionation approach to get rid of these impurities from the the liquid solution.
Okay. And sir, the next question is how secondary oil recovery can be increased?
Yes, there are various approaches. If you see the actual the approaches followed by the oil explorers, they in fact use blend of different recovery methods. It is not one single method which can guarantee you say the increased oil recovery. So they try out with various possible strategies, again based on the the pattern, the scenario, or the what you can say the geological factors underneath the earth, because oil sometimes can be distributed in more than one place. In that case, you need to adopt a different strategy. But so far, what has really worked out is with the pumping of steam and carbon dioxide, because steam is something which can be produced the vicinity of the oil production site, because you can divert part of the crude oil which you get into making of steam, generation of steam, which can be pumped in so that you dilute basically this crude oil, and so one can enhance the the sweeping of oil. And the other option is, of course, carbon dioxide. That's in fact has captured the attention of oil explorers, because you not only try to sweep the oil out, you're also trying to sequester carbon dioxide. So, for example, carbon dioxide which is generated outside, say, which is considered as a polluting component, can be fed into earth to recoup, in fact, a good amount of oil.
Okay. So thank you very much, sir, for giving answer.
Thank you for this opportunity, and thank you to the organizers who have arranged this wonderful workshop. In fact, it has been very kind of informative to all of us. It's a kind of a common platform for all experienced researchers and the researchers like me to share our works.
Thank you very much, sir, for your valuable time also.
Thank you.
So our next speaker is Dr. Bhaskar Singh. He is Assistant Professor, Department of Environmental Science, Central University of Jharkhand, Ranchi. Earlier, he worked as Assistant Professor in Department of Environmental Science, Central University of Rajasthan. He completed his PhD from Department of Applied Chemistry, IIT BHU, on the topic Development and Characterization of Biodiesel from Non-Edible Feedstocks. And he did his postdoc from Durban University of Technology, Durban, South Africa. He is a reviewer for the several international journals of Elsevier, Springer, and ACS. He has been awarded Pondicherry University Gold Medal during MPhil. He has co-edited 2 books with Springer publishers titled Algae and Environmental Sustainability and Phytoremediation Potential of Bioenergy Plants. His publications include 46 research papers and review papers in peer-reviewed and high-impact international journals, along with 17 book chapters with reputed international publishers. As per Scopus, the current H index of publications of Dr. Bhaskar Singh is 24, with total citations of 3,280. Dr. Singh's current research interest lies in the synthesis of biodiesel from plant, used cooking oil and algal oil, synthesis of nanocatalysts, and other novel heterogeneous catalysts for production of biodiesel. So without delaying, we move to the speaker. Sir, can you listen me?
Yes, I can listen you.
Yes,
am
sir.
I audible?
Yes, sir, you are audible, and we can see your PPT also, sir.
Okay, nice.
Yeah, thank you very much, sir. Now, sir, it's over to you.
Thank you for such a nice introduction. Very thank you to thanks the organizing committee for inviting me to deliver a talk on this very relevant topic, waste to bioenergy faculty development program organized by the Sharda University and the Maharashtra Institute of Technology jointly. So thanks a lot. So let me begin with my topic, which I have taken a generic topic: bioenergy production, opportunities and challenges in the present era. So let's begin with biofuels, which is the topic of this faculty development program. So biofuels, as we all know, it can be in any form, solid, liquid, or gaseous, and it is basically derived from the recently living biomass. So like here we can see a picture of tree, which takes oxygen and gives out carbon dioxide in the daytime and the process of photosynthesis, and in the night time reverse process takes place. And in this process, biomass is also synthesized. So this is how we get a biomass, and later on we will see how this biomass is converted to various forms of biofuels and what are the advantages, what are the limitations of all these biofuels. So biomass to biofuels, there are various level of feedstock which can be used to generate a variety of biofuels. So as we see that the biomass can be lignocellulosic biomass. Yes, and which comprises of forest waste. It can be a municipal waste. It can be a corn waste, and it can be starch or sugar, which is generated from corn or grain, or it can be lipids, which we can generate from either edible plants or non-edible plants, and the recently explored algae. So from these variety of feedstocks, we can uh, uh, develop different types of biofuels depending upon the processing that we adopt. So this processing can be uh, some form of pretreatment hydrolysis if it is for lignocellulosic biomass, and if it is sugars, we can directly go for saccharification, or we can go for fermentation, and we can obtain ethanol or butanol. Then if it is lipid, we can subject that lipid to a chemical processes, which is called as transesterification. Transesterification is a chemical process where uh, uh, triglyceride is broken into triglycerides and monoglycerides, and thereafter esters. And these esters are basically the monoalkyl esters, which we call them as biodiesel. So depending upon the processes, depending upon the feedstock, we get different types of biofuels. We can hydrotreat also, and we can generate renewable diesel also, and of course jet fuel also we can get from the different processes. So this is the pathway, as it is similar to the previous slide, that either we can subject feedstock to hydrolysis, biochemical process, gasification, even to pyrolysis, liquefaction, and or lipid extraction of these feedstock. So we can majorly we get three types of intermediate products: sugar, syngas, or lipids. So sugars we know are the best component for the synthesis of ethanol. Syngas in itself is a fuel comprising of carbon monoxide, hydrogen, and further we can make hydrogen from it. We can make methanol from it. And if it is lipid or oil, again, we can subject it to various processes, either hydroprocessing, hydrotreatment, or transesterification. If we subject it to transesterification, we can obtain biodiesel. And if we subject it to hydroprocessing, we can get renewable diesel or green gasoline or aviation fuel. When biodiesel is synthesized, the advantage is that we get a variety of co-products also. That the major one is glycerol, and apart from that, alcohol can also be generated. Or if it is a biorefinery approach, the leftover feedstock or the portion of biomass from where oil has been extracted can be subjected to generate a variety of biofuels, which can range from either biogas or biochar, or can be used for animal feed also, or can be used to generate electricity also. So the drivers for biofuel production, of course, we know that there is energy security issues, there is environmental pollution issues, there is the issue of climate change, there's issue of uncertainty in the price rise. We can see that the petroleum prices and the diesel prices are on a rise in the recent period of time. And then the deteriorating energy return from fossil fuels. The biofuel mandates are there. Recently, the government of India has mandated that in the coming year, by 2030, a significant portion of the mineral fuels, particularly the diesel and petrol, must be blended with a portion of ethanol or biodiesel. So the mandate is that it will start from 5%. Right now, it is very less. For biodiesel, the current usage is around 0.2% only. So that is also one of the things. Then checking desertification, developing the rural economy, and there are other indirect drivers also, which are essential, or which drive us to focus on the production of biofuel. This is the slide which depicts that because of the rising population, there is an increased economic activity. There is a significant increase in the demand of energy. Both renewable and non-renewable can meet this demand, and both of them are the sources of energy. But the limitation with non-renewable fuels, which is primarily fossil fuels, that they have a limited availability, limited stock. So they are going we are going to exhaust them in the ensuing years, maybe 50 years, 80 years, 100 years. But after that, we will exhaust them. So we have to move on now itself to the renewables. So they are always replenished. And just 1 minute, this call I have to attend. Hello. प्रियंका जी, अभी आपका हम अभी ऑफिस में हैं, बाद में बात करेंगे. ठीक है, ठीक ठीक ठीक, हम बाद में बात करते हैं आपसे. Yes. So renewable energy sources will never get depleted because we get it from the plant, which we can generate it. It's a conditional renewable resource. So if we plant more of the trees, if we plant more of the plants, we can keep on getting all these renewable resources. So bioenergy is one of them. There are other resources also: wind, hydropower, solar, geothermal, as we all know. One of the disadvantage with bioenergy is that it requires a bulk demand of bulk chemicals and materials. Because if it is biodiesel, we require enough of either methanol or ethanol. If we have to develop it from algae, we will require a sufficient amount of media, nitrogen sources, phosphorus sources. Then we require some materials also. We will require electricity also to synthesize that product. So that is one of the disadvantage with bioenergy when we compare it with other forms of energy like wind or solar or geothermal. So coming to bioenergy, as we know that it is can be derived from recently living organic materials, which can range from forest or crop residues. It can be agricultural crops and residues. It can be even sewage. It can be industrial residues. It can be animal residues. It can be municipal solid waste also. So we can see that a variety of waste also can be used as a resource in the production of bioenergy. That is one of the major advantage of bioenergy. So we all know that coal, petroleum, and natural gas are not biomass because they have been formed millions of years ago because of the processes. Then they are the transportation fuels. Biomass has a significant potential to be used as a source of heating or power generation. It can be converted into oil or gas also. And liquid biofuels are the most commonly one which can be used in transport sector. So it can be a supplement also. It can be used in lead form also, and compression ignition engines, or even in spark ignition engines. So there is two types of biomass. One is traditional and another is modern. So modern biomass excludes of biomass as fuel load because of the disadvantages that the energy density is very less. It's polluting also. So we have to concentrate the biomass, and biogas is one of the form. Liquid biofuel, ethanol, and biodiesel are the forms of modern biomass. Then we have different forms of bioenergy. It is in form of solid, it is in the form of liquid, it is in the form of gas. So if it is solid biomass, then it is basically derived from renewable resources. The liquid bioenergy is basically derived from the plant and animal sources, whereas the gaseous one are the common ones are methane and methane, which is derived by the breakdown of biomass using bacteria, a range of bacteria, which involves in the hydrolysis process, acidogenesis, acetogenesis, and lastly methanogenesis. So it can be these types of bioenergy have got different applications. So solid one can be used and direct use in gasification and in conversion technologies. The liquid one can be mixed with the conventional forms of fuel like diesel or gasoline, and the gaseous one can be used in form of energy in various applications at a small scale. So at a regional scale, this gas bioenergy can have their a very utility. So it can be from municipal waste, from landfill waste. And the examples are for the solid one, wood, sawdust. If it is liquid, the common ones are bioethanol, biodiesel. If it is gaseous one, the most common one is biogas and syngas and biopropane. So here we can see that this bioenergy uh, is being produced from the modern biomass, and it captures the carbon dioxide from the ambient air. So it is one of the major things apart from the oceans and biomass are the two major sources for the sink of carbon dioxide, which is a major greenhouse gas which causes climate change. So there are three things that we need to know about this carbon, the processes that we use. One is carbon positive, and there's carbon negative, and the third one is carbon neutral. So the conventional fuels that we are using right now, either it is crude oil based, mineral diesel, or gasoline. So these fuels are carbon positive. This means that the net carbon in the ambient air will increase when we use such type of fuel. But if we use a better fuel, a renewable fuel, so we can make the process a bit neutral. This means that the carbon that we are uh, emitting in the ambient air will get neutralized by the biomass, which is sequestering this carbon dioxide. So there will be no net emission or net release or net addition of carbon in the ambient air. So carbon negative is the best way out if possible. This means that the carbon will decline in the ambient air. So most of the processes, even with biofuels, the process, we cannot say it is carbon negative, because we do use electricity in the generation. We do use different chemicals which have some carbon positive impact on it. So our aim must be either to make the process at least carbon neutral or reduce the carbon uh, in the ambient air. And if possible, the best way is to have a process which is carbon negative. So if we see the scenario of various countries, here we can see that the renewables, which varies from hydropower, wind, bioenergy, solar photovoltaics, and others. So the ratio of bioenergy is significant in most of the countries, in European Union and Brazil, India as well, and United States as well. The bioenergy is a major source of renewable energy. Because of its easily accessibility or availability of the feedstock, or the generation of the waste, because waste is something which gets generated in everywhere. So this has been explored to divert or to use that waste resource in the form of energy. So if we see the global energy consumption of the world, so biomass, which is depicted in green color, so it's almost half of the percentage of all the renewables which are being generated worldwide. So half of the renewable energy in 2017 came from the modern bioenergy. So this bioenergy can be used in almost all the sectors. We can use this in transport sector, and of course heat generation, and for generation of electricity also. And likely other forms of energy can also be used in all the three components. Some of the leading countries which is based on the biofuel production in the year 2018. So that's US leads the usage of biofuels, followed by Brazil, Indonesia, Germany. Our country is way behind, but we have to think over it. So coming back to biofuels, there are two types of biofuels. One is primary and the other one is secondary. So primary biofuels has been used since ages by our forefathers in the form of forest products, in the form of animal waste, in the form of crop residue, but they have a disadvantage that they are polluting. They generate some particles, some respirable particles, which, if injected in our body, can have adverse effects. So the secondary biofuels are superior biofuels, which forms in the category of first generation, second generation, and third generation. So the first generation biofuels were mostly from the feedstock, like which were edible, like wheat, potato, barley. So there was a issue of food versus fuel. Then came the second generation biofuels, mostly from the non-edible feedstocks like jatropha, karanj, miscanthus, grasses. Again, they had some limitations, like miscanthus. It was difficult to convert them into biofuels. More energy is required. Then again, there was land versus fuel issue. Then came the third generation biofuels, mostly from the microorganisms like microalgae, yeast, even fungi. So these microorganisms require very less land area or minimal land area. So they are more preferable. So if we see the comparison of these three fuels, first generation, second generation, third and fourth generations. So we get different types of products from these fuels. So the fourth generation one comes from the production of, which is produced from photobiological solar fuels and electrofuels from solar energy. So which are basically hydrogen, methane, and bioethanol. So we have moved now to fourth generation fuels. Then we have we can see that the first generation biofuels have certain limitations, that they are basically edible ones. They are generated from edible feedstock like rapeseed, soybean, sunflower, coconut oil, and palm oil. So the three types of first generation biofuels commonly, which had been derived from the edible feedstock, were biodiesel, bioethanol, and biogas. So coming to biodiesel, it's a very good fuel in the sense that it is non-polluting, or we can say it is lesser polluting. It is derived from the non-edible feedstock, variety of feedstock. It can be a waste cooking oil as well. It can be a waste fat also from animal parts. It can be from algal oil as well. So biodiesel is a substitute of diesel, and it can be used up to 20% blending without any modification of the engines. So it can be used in compression ignition engines without any modification when it is blended up to 20% with the mineral diesel. And if we go beyond that, so some modification in the engine may also be needed. Then bioethanol could also be produced from sugar and starch by fermentation, and then by anaerobic digestion, one could get biogas or biomethane. So I will skip this slide. First generation process we all know. So coming to biodiesel. So biodiesel is a long chain alkyl esters ranging from C16 to C18. So the first compression ignition engine, or the first engine, basically ran on a bio oil. It was not a biodiesel, but it was a biofuel. It ran on peanut oil in the year 1900. But later on, when diesel was found, when crude oil was found, so this got neglected. And later on, when we realized that this crude oil is polluting, it is less in quantity, we will get exhausted in the near future. So right now, since last few decades, since last 10 to 15 years, we have focused extensively on production of these renewable fuels like biodiesel and bioethanol. So it can be produced by two ways. One is by alkali-based trans-esterification, or it can be produced by acid-based trans-esterification also. So during this process, 3 moles of biodiesel is produced from 1 mole of the oil, and glycerol is also synthesized for every mole of converted triacyl glycerols. The process requires a catalyst for a fast reaction, because otherwise it will take a very long time for its production. This alkali catalyzed reaction can be catalyst can be homogeneous, can be heterogeneous as well. Homogeneous are very fast, but heterogeneous has the advantage of reusability. The other type of catalyst which is highly efficient is enzymes. So it is these enzymes are highly selective. It's highly pure, so it is highly specific also, and it requires fewer, very less process steps as compared to chemical catalyst. But the major bottleneck right now is its high production cost. So if we can bring down the cost, we can have a biodiesel production which is comparable to the production of crude oil. So coming to advantages, it is non-toxic, but not completely non-toxic. Some of the toxic elements are there, like some carbon monoxide will get generated, some amount of hydrocarbons may also get generated, but it is comparatively very less, because toxic elements are excluded here. Like one will not get any sulfur from this biodiesel combustion. One will not get BTX compounds like benzene, toluene, ethyl benzene, or xylene. It is biodegradable. So like we have spillage of crude oil during transportation in the marine ecosystem also. So if this biodiesel gets spilled, it is biodegradable and it is good for the environment as well. It's highly miscible, so it can be used at any ratio with the mineral diesel, and it has a reduced amount of carbon and higher hydrogen. So its calorific value is a bit less. But because of this oxygen content, it has got better combustibility. So but with a better combustion, there is a lower emission of particulate matter and also a less emission of carbon monoxide. So it reduces the climate, it mitigates the climate change and the global warming as well. So as discussed, that low sulfur will be emitted. Some of the disadvantages are also there with biodiesel. The major one is the increased amount of emission of NOx, and that is also a major issue. It's a major pollutant. It's a primary pollutant. It can also lead to formation of secondary pollutants like photochemical oxidants, photochemical smog. So research is needed to reduce this generation of NOx. The major bottleneck is the high feedstock cost at present, because even microalgae require photobioreactors for its production. So we have to bring the cost of production at par with that of mineral diesel. Then only we can make it marketable. And of course, it has got a bit lower energy content as compared to the mineral diesel. So similar is the advantage with bioethanol also, carbon neutral, biodegradable, renewable. Disadvantages of bioethanol, it requires large land area if we have to get the feedstock. Advantages of biogas, we all know that we can get biogas from various waste materials like human and animal waste also. Disadvantages is a higher capital cost. Methane, we know, is a fuel which can get auto-combust, it can get auto-ignite if it is in the environment, if it is released in the environment somehow accidentally, ranging from 15% to 16%. So there can be some explosion also if it is not handled properly. It needs regular monitoring, regular proper handling is needed for that. So coming to second generation biofuels, they have got a competition with the food crops. That is the major bottleneck with it. It can be overcome with some type of grasses, switchgrass, and fast-growing trees. But again, these fast-growing trees have again some issues with them, particularly eucalyptus, that they extract water from the groundwater, so they deplete the groundwater. So there are various issues with the second generation biofuels also, but better than the first generation biofuels. So we all know about this. I will skip some of the slides. So this is the process of lignocellulosic biomass residues. We can see some waste materials from landfill waste, or the crop stubble. Like we know that there is an issue of burning of crops by the farmers. Uh, so if they can be they can be taken and pre-treated, hydrolyzed, they can be used in the production of biofuels, biogas, even paper and pulp. So then this is the process of conversion of lignocellulosic biomass to ethanol. I won't go into much details. So you can see that there are various processes, thermochemical as well as biochemical. So by these processes of thermochemical and biochemical, we can generate biodiesel, or we can get syngas, carbon monoxide, and H2. Then pyrolysis oil, we can get, which is called as bio oil also, and we can generate heat and electricity from that these processes. We can generate electricity also from the biomass, particularly from the municipal solid waste. So coming to third generation biofuels. So this comes primarily from the microalgae, and this is non-food feedstock. Of course, microalgae algae has been used as an animal feed also. So they are more productive. So more amount of microalgae can be produced in a small land area. Whereas if we go for the first generation or the second generation biomass, we will require a large land area. So basically, it does not compete with the food crop, and more amount of biodiesel can be prepared from a small land area. So it is a project for the future and not of the present, because of the cost intensive process. Because if we go for harvesting in a raceway pond or in an open pond, various environmental factors are there, which is a limitation right now, because microalgae requires sufficient amount of carbon dioxide. If oxygen or pH or the sunlight get fluctuated, so we won't get the desired microalgae culture. So for that, we do require photobioreactors right now, and which is costly. The process is costly at the moment. So if we could overcome this this cost intensiveness of the process, in the coming future, we can have a biofuel which will be more competitive in the market. So this is the process of biodiesel production from algae. Algae, if we devoid them of certain nutrients like nitrogen and phosphorus, so what it does, it starts accumulating more of oils in its cells. So that is our focus area. So with more of oil, we can have more of biodiesel. The yield will be higher. So this is the processes of biochemical conversion, thermochemical conversion, and chemical conversion. So from the solar energy, we can have oil extraction. We can have algae, which can bear oil. We can have biodiesel. We can have glycerin as a byproduct. It has got numerous industrial applications. Coming to the fourth generation biofuels. So fourth generation biofuels is basically the genetic engineered organisms. So if we can manipulate these microalgae, if we can inject certain genes in those organisms, which will try to accumulate more of oil, then it will be beneficial to us. So it will be more of the aim is more to make the process more carbon negative by creating artificial carbon sinks. So this is the processes. So here's the comparison of first, second, and third generation, which I think we had some of the parts we have discussed. All of the process are environment friendly, but of course the first one has some, first and second one has some competitiveness with the food crops, and the third one is more beneficial, more environment friendly, because there is no conflict of food versus land. It offers higher growth rate also, higher cell lipid accumulation also, but there are certain challenges also with the third generation feedstock also, because of the high initial production cost involved. So evaluation of potential feedstock for biofuel production. So the feedstock must be at a low production cost, because 70%, 60 to 70% of the cost of biofuel production comes from the feedstock. That is why we need to have a low cost feedstock, low carbon footprint, low water footprint, low input of nitrogen, less tolerance, high tolerance to biotic and abiotic stress, easy conversion to biofuel, preference of non-food and non-rainforest plants. Because if we see the scenario of Brazil, Brazil has been one of the major leader in generation of bioethanol. But what Brazil has been doing in recent times is that they have been clearing rainforest for planting biofuel crops. That is also not good for the environment or for the ecosystem. That's not preferable. So we need to look for those land which are either marginal land or wasteland where we can plant those biofuel crops. So the key benefits are sustainability, flexibility, energy security, mitigation of climate change, and all. And the key challenges are to ensure sustainability, to safeguard food security, to protect biodiversity, to manage competition for land and water, to control pollution, and to remove barriers to biomass and bioenergy trade. So these are the currently used non-edible plant oil for biodiesel production: jatropha, Pongamia pinnata, tobacco, Maduka longifolia, neem, castor bean, camelina. So all of these are non-edible. So what we have to emphasize is that we must look for those marginal lands which can accommodate or which can bear those biofuel crops with minimal input of materials, minimal input of water, minimal input of fertilizers. So we had discussed these are the major advantages of biofuels. But all the biofuels, biodiesel, bioethanol, biohydrogen, biomethane, all of them are renewable. They are biodegradable. They are less toxic. They are miscible with fossil fuels. It can generate employment opportunity. They have got better lubricity also, devoid of sulfur, energy security, carbon neutrality, wasteland reclamation, and the biorefinery approach. So in a biorefinery approach, we get various projects from a single product through a circular economy. So barriers, as we know, high production cost, and we have to improve the EROI, that is energy return on energy invested. So it must be more than one. So if you are investing 1 unit of energy, we must get more than 1 unit of energy. Lack of feedstock, lack of industrial data, uncertain techno-economic viability, life cycle impact assessment, poor policy structure, capacity building of local stakeholders. These are the barriers. Some of the research work ongoing in our lab is use of waste materials in the production of biodiesel. So we have tried to use waste materials like cement waste as a catalyst. So because catalysts play a major role. So if we use virgin catalyst from the industry, so that will add to the cost, and that will make the process less sustainable. So using waste materials in whatever processes as a catalyst or for the as a feedstock or at any other stage, so this can make the process more sustainable. So we have utilized cement waste, which contains calcium oxide. So calcium oxide, it forms methoxide ion, then it attacks the carbonyl carbon of the triglyceride, and it leads to the formation of an intermediate. Then this rearrangement of that intermediate leads to the formation of monoalkyl esters. Then we have used some other catalyst, barium zirconate and cesium doped zirconate as a catalyst also for production of biodiesel from Militia pinnata. It's basically a Pongamia, that is current local name. Then we have tried to enhance the oxidation stability of biodiesel, as well as to enhance the cold flow properties of the biodiesel. See what happens that during winter season, the fuel it solidify. So particularly biodiesel, as it contains significant amount of um, unsaturated components, so it can solidify during winter times. And if there is the unsaturated components or unsaturated bonds, so they may get auto oxidized. So what happens, there is a inverse relationship between these two properties, cold flow properties and oxidation stability. So if we enhance the cold flow properties, we have to compromise on the oxidation stability, and if we enhance the oxidation stability, we have to compromise on the cold flow properties. So by doing winterization and by adding some plant phenolic additives, we have tried to make both these properties at par, at par or in the specification, as per the specifications of Government of India, which is IS 15607, as per ASTM, that is D656751, so that it meets the specifications and can be used as a fuel. Then we have tried to use green tea, the extract of green tea, to enhance the oxidation stability of biodiesel, which we have produced from waste cooking oil. And then we have tried to synthesize calcium oxide in nano form using sol gel method, because nano catalysts offer a better surface area, a high surface area, high porosity. So somehow we have tried to use in the waste materials, or try to enhance the catalytic activity, so that we get a product biodiesel which is better in terms of its marketability. Somehow we can reduce the production cost. That has been our aim in our work. In one of the work, we have tried to use solar light to heat our reactors or the reaction components, because if we have to produce biodiesel through transesterification, we need to heat our components of which comprises of triglyceride, methanol. So if we can use solar irradiation, because India is a tropical country, and particularly in the summer season, we get enough of solar irradiation. So we can use that to make our product economical and more viable. So thank you for your patient hearing. Thanks a lot.
Thank you very much, sir, for this wonderful talk. So now there are some questions from participants.
Yes.
So first question is, which pre-treatment method can be preferred for bioenergy generation from biomass?
See, pre-treatment method will depend upon the feedstock which is being taken. So, example for bioethanol, if the feedstock is say lignocellulosic biomass, so the pre-treatment can be acidic pre-treatment using HCl, using H2SO4. It can be acid alkali also, NaCl. So depending upon the product that is desired, depending upon the feedstock, the pre-treatment will vary. Pre-treatment can be also done by autoclaving, by hydroclaving, by microwaving. So we have, if it is bioethanol, we have to make the product in such a way that it is we get sugar from that product. So it can be fermented. So depending upon the feedstock, depending upon the product, the pre-treatment process will vary.
Okay. Okay. Sir, next question from participant. Why biogas is more popular technique in rural parts as compared to other bioenergy techniques such as biofuel?
Yes, that is true. Biogas is more because earlier there was this concept of bioethanol and biodiesel have come up very recently, and the structure which we call as the dome structure has been established way back in when our country got independence. So we already have a structure, and from where we can have a waste product. We can have cow dung, we can use cow dung, we can use human excreta also. And the process is a bit simpler. If we have to establish a bioethanol plant, if we have to establish a biodiesel plant, we will require infrastructure for that. We will have to build a plant for that. will the technique, the infrastructure will be needed, trained manpower will be needed. Whereas for biogas, the process is a bit simpler. You just need to make a structure for that, and then all types of waste materials, biomass or the human excreta or the cow dung can be used.
Okay. So, sir, next question is, can we recover bioenergy from released carbon dioxide from industries after combustion?
Not directly, but indirectly. Why not directly? Because with carbon dioxide, what we can do, and many places the work has been in progress also, that carbon dioxide is captured and then utilized to culture microalgae. So directly from carbon dioxide, the biofuel is not preferable, but using it to produce or develop or grow a feedstock, which will later on will be used for biofuels.
Okay.
Yes.
So thank you very much, sir, for this wonderful talk and for giving your valuable time for this FDP. Thank you very much, sir.
Okay, thank you. Thank you to you also. Thank you to the organizer for giving me such a chance to have a talk with all of you.
Yeah, thank you very much, sir.
Thank
So,
you, Bhaskar Singh. Thank you.
Yes.
yeah, so I thank a lot to the participants for attending this afternoon session. Your active participation made this event viable and interactive. And in the next session, like tomorrow, we will meet again at 10 a.m. for the morning session. So thank you very much to all the participants and have a good day.